This is lecture 23, and it's the first of the lectures on optimization or on max-min word problems. So we're going to look at the problem of solving maximization or minimization problems. That is, finding the most or finding the least, which sounds like what we've been doing lately in graphing, finding the absolute max or the absolute min for a function. So we're going to do that, though, in the context of word problems. So these are the harder word problems. And the first hard problem, the first hard part here that we come to is that you don't even know what the independent variable is anymore, because t, time, is usually not even a variable in these problems. So it's going to be difficult. So rather than focusing on the independent variable, I suggest that at first you try to think about what the dependent variables are. And then at some point an independent variable will emerge. And I'll try to explain how we're going there. But otherwise, the procedure for solving problems is about the same as it was before. So let's look at an example, and we'll work through it that way. It's an example that's similar to one in the book, but very slightly different. Okay, you have 500 feet of fencing that's to be used to fence off a garden. The garden is to have a rectangular shape, and on one side it's to be along a river. You don't need any fencing along the river. What are the dimensions of the garden that will give you the most possible area? Now, you read through that until you understand it. That's the first step. And then the next thing that we try to do is to draw a picture. So I'm going to draw a schematic picture, that is, something that doesn't try to be what's going on too much. This is the river here. Whoops. Sorry about that. Forgot to flip this back to my pen tool. All right, so here's the river along here, and I'm just going to draw it that way. So this is the river. And the garden is going to be along the river here, so I'm just going to fence it off, and it's rectangular. So I don't know what it looks like, except it's a rectangle. And I don't need fencing along the river, so it's like the fourth side is going to be along the river. So this is the garden here, and the question is, what are the dimensions of the garden that will give you the most possible area? Well, I've drawn the picture, and I've got to focus on what they ask me, usually the bottom line. What are the dimensions? What are the dimensions of the garden? So if you look at the garden, what are the dimensions? Well, the dimensions of a rectangle are the length and the width. So I could call them L and W, but I prefer X and Y. So I've got X this way, Y this way, and of course Y this way. And I have X this way, except that I don't have any fencing here. I'm going to use the river along the fourth side. Okay, so that's the picture, and now I need to figure out what it is that they want me to do. And they're saying, what are the dimensions, in other words, what's X and Y, so that I'll get the most possible area. I don't have an area written down here, but the area refers to the area of the garden, and I know how to calculate the area of a rectangle. The area of a rectangle is length times width, so that would be just X times Y. So my problem is to find the most possible area. So this is what you should do. This is a problem in maximization. So what you say is maximize area, and we'll call this A. So we want to maximize A, and we get to control X and Y. So if A is a function to be maximized, we want to think of it as a function that's dependent upon things that can be controlled. So what can we control in this? Well, we can control how much we go this way, and we can control how much we go this way. Well, if I want to maximize the area, what's to stop me from building a garden that's really, really big vertically and really, really wide horizontally? Well, there's something in the problem that stops me from doing that. There's a constraint in the problem, and it's the very first sentence. You have 500 feet of fencing. So I can make it as long as I want, but you only got 500 feet to work with. So that tells me that no matter what I do, this all together has to add up to 500. So I can write that down. If I take Y plus X plus Y, that has to come out to be 500. That's all I've got to work with. And of course I can simplify that, X plus 2Y. equals 500. All right, so this is my function, and at the moment it seems like it depends on x and y. And here's where I get a chance to choose my independent variable, because I can see already that a depends on x and y, and I get to control x and y, but they're really not independent of each other. In other words, if I choose y to be very big, then I'm going to have to make the garden a little bit shorter this way, right? Or if I choose to make y very small, then I could make a very long garden, but I want to make the most area. So what I'm saying is x and y are not independent of each other. If I increase y, x is going to have to go down, and vice versa. So I get to pick which one to make my independent variable. And being lazy, I look at this equation and say, you know, I could solve this equation pretty easily for x. X equals 500 minus 2y. And then that allows me to replace x up here by this expression. So I would have this for a. A is equal to, x is going to be gone now, so it's 500 minus 2y times y. And you see what I've done? I've taken this function a that is a function of x and y. A depends on x and y. And now I've turned it into something that depends only on y. So I could think of a here as a function of y. Right. And so now I have a standard kind of calculus problem. I want to maximize, I want to find the max, the absolute max for this function a. And one of the things that you should do is take the time to really think about what are the constraints on this function a. What makes sense for numbers y? What's the least that you can make y? What's the biggest that you can make y? And you can tell that just from here and from looking at the picture. So sometimes you have to integrate in the information that's given. In this problem, it's pretty easy to just look at this and tell what's going on. The value for y obviously has to be bigger than 0. You can't choose to make y 0. Well, you could just put the fence that way and then you'd have 0 area. But also, you can't make y too big. If you made y, think about this, if you made y 250, then putting 250 in for y here, you get 2 times 250, which is 500. Subtracted from 500 gives you 0 area. So your y has to be less than 250. So these are kind of like endpoints. I'll put less than or equal to, but you should check endpoints. In this problem, it makes no sense to check the endpoints because you know that those endpoints are going to give you minimal areas. But if the problem had been find the minimum area, then yeah, the endpoints would give you the answer. But here, you can see that if you made y 250, then you'd eat up your entire fence just going this way and then back the other way, and you wouldn't have any room for any horizontal distance at all. Okay, so we know that our function a is 500 minus 2y times y. Now what kind of function is this? Well, if you multiply it out, you can tell. Most of you already know. It's 500y minus 2y squared. So this is a parabola that opens downward. And I know everything there is to know about these guys. So it's a parabola that opens downward, and I need to find the maximum, which is right up here, where the derivative is going to be equal to 0. Obviously, the endpoints are giving me points down here where I'm getting 0 area. So this is the area function viewed as a parabola. Okay, so where is the derivative equal to 0? Well, I calculate the derivative. A prime would be 500 minus 4y. And I set that equal to 0 and solve for y. So 500 equals 4y, or y equals 500 divided by 4. What is that? 1. 4 into 10 goes 2, with 2 left over, 125. So y equals 125. So that tells me that when y equals 125, that's the value where the area is going to be maximized. And if I plug that in here, I can see that I get 125 going this way, 125 going this way. That's a total of 150, and that leaves me with an extra 250 this way, which I could tell if I plugged the 125 in here, and I get 2 times 125 subtracted from 500 gives me the 250 that I just gave you. And this will be my absolute max. So that's the solution. X equals 250, y equals 125. So the dimensions, read back to the original question. If you look at the original question, the question says, what are the dimensions of the garden that will give you the most area? And now we know the dimensions are 125 by 250, or 250 by 125. Okay, let's turn our attention to one other problem for today, and this is my favorite problem in this kind of thing, and this is what I call the ideal beer can. So here is the ideal beer can problem. Beer can is to be constructed from a sheet of metal by cutting out 2 circles to form the top and the bottom, and a rectangle that you roll into a cylinder to form the side of the can. If the volume is supposed to be fixed by law and cannot be changed, what dimensions of the can will result in using the least amount of metal as measured by square inches of metal actually used? Now, you might pause this and reread that a couple of times just to understand what we're talking about. That would probably be a good idea. Now, how do we think about this? Well, again, draw a picture. You're going to draw a can. Well, you may not be able to draw a can. I'm not very good at drawing, and especially with this thing that I'm working with as an input device, this is about the best I can do. There's my can. Now really, how is that can being made? It's being made from 2 circles, one for the top, one for the bottom, and then there's a rectangle that is cut out like this, and then you take that rectangle and roll it, just roll it, and then weld it together along the side. So when you do that, you form this cylinder, and then you pop the top and the bottom on, and that's your can. Now I know the cans aren't made that way, most of them, but this is an old problem, and it also is an interesting one. And really, even with the ways that they are made, you can analyze in similar ways. Okay, so this is how the can is made, and we read the problem and find out what is it that we're being asked to find. The volume is supposed to be constant, fixed. We can't change it. What dimensions of the can? So here we go again with the question of dimensions. So what are the dimensions of a can, of a cylinder? Well, there are 2 of them. There's the radius, and then there's the height. What dimensions of the can will result in using the least amount of metal? So that's where I focus on, where you see words like max, min, most, least. I want to use the least amount of metal. So I want to use the least amount, or minimize something. That's what I'm looking to do. I want to minimize something. And the amount of metal, I'm just going to call it A. This time it's the amount, amount of metal, and we're going to call that A. Now I need to represent A in terms of what's here. And I can do that because if A is the total amount of metal used measured in square inches. Now this takes some understanding, and when I was a student I didn't have any of this. If you go out and buy sheet metal, you buy it in sheets, and you buy it by the square foot or square inch or square meter or whatever. So the idea is that it has a certain thickness, a uniform thickness, and then you buy it by the square whatever. So I want to calculate the amount of metal in square inches. So the amount of metal is the area in square inches of that circle, doubled because I got a top and a bottom, and then the area of that rectangle. And the height of that rectangle is just h. I already know that. And the length of that rectangle is what? Well, let's go back to the circle first. Easy questions first. I'm getting ahead of myself. The dimensions of the circle are just the radius. That's all I need. And that's what I wrote in here as r. So the circle has dimension r. So the amount of surface area, the area of that circle, would be, of course, pi r squared. And to get the area of this rectangle, I'd have to go the height times this distance. What is that distance? I could make up a variable for it because I don't know, or I could recognize that this length here comes from going around the can this way. So really, that sheet is just the side of the can rolled out flat. So the distance along here is just the circumference of that circle. And the circumference of a circle is 2 pi times the radius. So that tells me that the area of this rectangle is going to be this number, 2 pi r, times the height. In other words, length times width is the area of a rectangle. So the total amount of metal would be this number, 2 pi r h, plus the areas of these two circles. Each circle is pi r squared, and I've got two of them, so I've got 2 pi r squared. Okay, now we haven't worked everything into the problem just yet, but let's sit back and pat ourselves on the back in terms of what we've done. We recognize that the problem is to minimize something. That's very important. Always focus on what it is that you're supposed to maximize or minimize. In this case, we are minimizing not the dimensions like we were in the first. Well, we weren't minimizing dimensions. We were maximizing area in the first problem. Here we are minimizing the total amount of metal used measured in square inches. So we are minimizing this amount, which you could say is the area, the total surface area of the metal. And the total surface area of the metal comes from top and bottom and the side. This is what we're using. So you add all that together, and that's your total amount of area used by the metal, and that's your dependent variable. So you can ask yourself now, what does this variable A depend on? And if you read across, here's a variable r, here's a variable h, pi of course a constant, and r again. So there's two variables. A depends on r and it depends on h. So if I'm going to minimize this, I need to look at the graph of it, but right now I can't do that because it's got too many variables. I've got r and h. So I need another relationship among the variables, just like we've always done with word problems. I need another equation that relates r and h. And the clue for that says it comes from the second sentence that tells us the volume of the can is fixed by law and cannot be changed. So that means the volume of the can is constant. So V is constant, where V is the volume of this can. And you've got to know what the volume of a cylinder is. So V equals, well, it's a regular solid, which means it's just a shape and then it's lifted straight up, vertical sides. So the volume of any regular solid is the area of the base times the height. So that would just be pi r squared h. Many of you have that memorized already. The volume of a cylinder is pi r squared h. Okay, but it seems like we're introducing a new variable, v. But see, the thing is, v is constant. You'll see in some problems they will tell you v is 100 cubic inches or something like that. Whatever it is, it's what it is, and it's a constant. For me, I would rather just use the letter rather than having numbers muck up the problem, because it's so much easier to carry this letter than it is to write 128, or whatever it is, especially if it's got decimal places. Okay, but this is an equation now that relates my variables r and h. So what I can do is solve for one of the variables and stuff it back in here. And it seems to me like it's pretty easy to solve for h, so that's what I'm going to do. So h is equal to v divided by pi r squared, and I'll put that back up in here. So that tells me that a is equal to 2 pi r times this, v over pi r squared, plus the second part, 2 pi r squared. If I did that right. Okay, so now I've got it to the point where a is a function of a single variable. How did that happen? A is now a function of r. You can think of it that way. It happened because I can't independently change r and h. If I scrunch up at r, if I make r smaller, I'm going to have to make h bigger because the volume of the can is constant in this problem. That's important. If they tell you the volume of the can is constant, then you have to use that somewhere. And that means that you can't just change r without also changing h, and vice versa. So because of that, I can eliminate one variable in terms of the other. Well, of course, I need to simplify this. So a is equal to, let's see what cancels. It looks like I get an r canceling, a pi cancels. So I've got 2v divided by r, right? The other stuff canceled. And then I've got plus 2 pi r squared. Okay, so this is my function a. And again, the constraints on this are that I cannot make r any smaller than 0. And at some point, I can make r too big, and it'll flatten out the can. I can't make h equal to 0 either. So that I could figure out what that is by looking at the equation for h. So at some point, r will be too big, and it'll make h equal to 0. So we don't want to run into those situations. But all we need to do now is figure out what the critical numbers are for this function, because this function is a little bit harder to calculate. And to look at a graph of it, I'd have to plug in a particular number for v, just to guess, to see what it looks like and draw a graph. So this is kind of a different sort of graph. We may look at it in a minute anyway. All right, so let's calculate the derivative and see what we get. The derivative is what? Well, how do I take the derivative of this? The easy answer is, remember that v is a constant, so this is 2v times r to the negative 1. So the derivative is going to be minus 2v times r to the negative 2. So it's minus 2v over r squared. Plus, the derivative here is 4 pi r. Oh, it occurred to me that I'm taking derivatives with respect to what? Well, the answer is obviously I've been taking derivatives with respect to r in this problem. Well, who decided that r was the independent variable? Well, I guess I did and never said it. I decided r was the independent variable when I chose to solve for h and put that in to my original equation here, because now a is seen to be a function of r. A is the dependent variable, and r alone is the independent variable, where before it looked like I had two independent variables in the problem. All right, so this is the derivative, and I set this equal to 0 to figure out what the critical numbers are. Obviously, r is a critical number because it blows this up, but r is not in the domain. So 0, r equals 0, excuse me, is not in the domain. So that doesn't count. So we set this equal to 0 and solve. I'm going to throw the negative term to the other side. So we get 4 pi r equals 2v over r squared. And I can divide both sides by r. No, excuse me. I'm going to multiply both sides by r squared to clear the fractions. Divide both sides by 2. So I'm going to get 2 pi r cubed equals v. And I can solve this for r. R will be equal to the cube root of v divided by 2 pi, whatever that is. So as soon as I know what that fixed volume is, I just plug it in here, divide it by 2 pi, take the cube root of it, and that's the value of r. All right? And so that would be the solution. And we really should check. I'm not going to take time to do this on the video here. You've already been suffering enough in this video. But I wanted to show you one other thing and leave you with a thought for tomorrow's class. And that is this one. Let's look at this in another way. What if we just substitute in what v is equal to from before into this in this equation that we have right here? Instead of solving for r, let's just put in what v is equal to. V equals pi r squared h. So if we go 2 pi r cubed equals pi r squared h, we could divide both sides by pi, divide both sides by r squared, and here's what we end up with. 2r equals, pi's gone, r squared's gone, h. So look at this, folks. The minimum amount of metal will be used when 2 times r is equal to h. 2 times r equals h. What does that mean in our picture? 2 times r equals h. That would mean that the distance across, in other words, the diameter, this is the diameter, of course, the diameter of the can is the same as the height. The diameter of the can is equal to the height? How many cans do you know of that are built like that, that have a shape where the distance across this way is the same as the distance across this way? All the beer cans I've ever seen look much more like this. So here's your thought question for tomorrow, and we'll talk about this a little bit during class. Why are cans shaped like this when it's going to be, apparently, they're going to use more metal using building cans this way than building cans this way? Right? This shape minimizes the total metal used. It does. If the can is just as long this way as it is tall, then you'll minimize the metal. But they're wasting metal by building cans this way for a fixed volume. Why do we do that? That's the question to think about for tomorrow. See you later.